Hey guys, so welcome back to 2.5 Implicit Differentiation. So if you saw my last video, it was an introduction. This is going to be the lesson for the actual implicit differentiation of your binder. So let's go ahead and start with the example number one. So I already explained what an implicit and an explicit defined equations are. So given this relation, differentiate with respect to t. Since you must apply the chain rule, each derivative will have a dy or x dt as part of the derivative. Let me go into more details of what this means. Taking the derivative with respect to t, this time we're not taking the derivative with respect to x. In my introduction video, I talked about that this is respect to t, or in the last video was x. Anytime that this variable does not match with the variables in your equation, then you have to apply a chain rule, because we don't know if y is a function of t or if x is a function of t. So when you take the derivative, you have to multiply it by a factor of what we think the derivative may be. Okay, so what this means is that taking the derivative of y cubed is 3y squared, and then apply the chain rule dy dt, because we're doing dt in the bottom. Y squared 2y dy dt, negative x squared negative 2x dx dt equals, well, what's the derivative of a constant? It doesn't matter what variable you're taking the derivative with respect to. The derivative of a constant, since it's no change involved, it's 0. So this is my derivative, and I'm done. So that's just a real quick introduction. The next example, we have w. I'm not going to spend too much time on this. Now we're just taking the derivative with respect to w. So taking the derivative with respect to w is 3y squared dy dw 2y dw minus 2x dx over dw equals 0. We don't know if y is a function of w or if x is a function of w. So we're going to assume that the derivative of x or y with respect to w exists. We're going to assume that it exists, and even if it doesn't, it could be 0, which means we just have 0. And you'll find out what I mean by if it exists or not later on. We're going to see more examples, something that's called related rates. The last part, taking the derivative with respect to x now, well, that is going to be 3y squared dy dx plus 2y dy dx minus, let me go ahead and break this one up over here. If I take the derivative with respect to x of a term that is x, using the chain rule, implicit differentiation, that we're doing up here, the derivative of negative x squared is negative 2x. If I use the implicit rule, I have dx over dx, which is just negative 2x. So really, you guys have been doing implicit just like the way you guys have been doing chain rule since the moment you've been doing derivatives. Equals 0. Now, I'm going to call this part D. Now use algebra to rearrange and solve for dy dx. Now, we all know that dy dx is the same thing as y prime. The reason why I make this statement is because it's going to be easier for me to write and to solve for dy dx. So I'm going to replace every one of these guys with a y prime because it's just easier to write. 3y squared times y prime. And the way I tell my students to do this is I always make them write a dot just to make sure that they're not confusing this y squared with a y to the first. And your primes, you have to know what your primes are. Just make them stand out. That's your prime. 2y times y prime minus 2x is equal to 0. I want to solve for dy dx, which is the same thing as y prime. So before I do that, let me add 2x to both sides, because we know that when we want to solve a variable, we isolate the variable and we start removing everything that's around that variable, but in a specific order. So we take care of the subtraction and the addition first. 2x is equal to 3y squared y prime plus 2y y prime. Now notice I have y prime and y prime. I can factor out y prime. Y prime is, well, y prime times 3 squared plus 2y is 2x. So if I want to solve for y prime, I divide 3 squared plus 2y. And this is my dy dx, because we know that y prime is dy dx, and that is the solution for part D. So I'm going to go ahead and stop this video here, and we'll move on to part 2 of the same lesson in the next video.